Hello everyone, welcome to COMP359, Design and Analysis of Algorithms. In this video, I'm going to review the sorting algorithms that you have already learned in COMP251. So we have talked about insertion sort, merge sort, quick sort, and heap sort. These are, the main famous sorting algorithms in computer science. There are a couple of features in about the sorting algorithms that we care about, and we wanted to see that if these sorting algorithms have these features or not. The first one is in place. We say that a sorting algorithm sorts in place if only a constant number of elements during the sorting will be stored, somewhere outside of the original array. It just basically means that we are using constant amount of information, a constant amount of space in addition to the original array to store the store the elements during the sorting. And the other feature is stable. So we say that a sorting algorithm is going to be stable in case you have two objects that they are going to be equal, and after the sorting, the order of them is the same as before. So let me actually give you this example here. So here in this example, you can see that, let me see that the pen here is not working. Okay, so here you can see that I have two elements, 8 and 8. After sorting the whole sequence, the first element of 8 is coming before the second one in the first actually sequence. So this sorting is going to be stable, unlike this sorting that you can see that the order of these two 8s has been changed. So if you are sorting some, integer number, some primary data, you might actually really care that, okay, so what's the matter? It doesn't really matter that if I'm changing the order of these two 8s. But, this feature, a sorting algorithm be stable, is going to be important when you are sorting some type of object that they are not the primary data type. So, for example, consider sorting, some the rows of this this table here. You can see that we have sorted based on the grade, right? And we are going to really actually care that, okay, the original all of these rows has been sorted based on the name first. Then we wanted to sort them based on the grade. So we want these objects to be sorted in a stable way, so that after sorting them based on the grade, still all of those that have the same grade are going to be sorted based on their name. So being stable is going to be important in some cases. So this is a feature that we are going to check if these four famous sorting algorithms have these two features or not. So the first sorting algorithm that we are going to review is insertion sort. So I'm not going to completely review the algorithms. If you wanted to review them, I have a video that I put the link to that on the Blackboard as well, that actually discussed about the insertion sort, quick sort, merge sort, and heap sort from COMP251. And you can also actually refer to your textbook about these sorting algorithms. So here I'm going to just check, quickly review them based on, and check that if they have these properties in place and stable or not. The first sorting algorithm is insertion sort. So remember that in insertion sort, uh, at each iteration of the main loop, what we consider is that we assume, for example, in this iteration, we assume that this part of the array has been already actually sorted. Then this item will be inserted in its correct position. And how it will be actually implemented, this is the most famous approach to implement the insertion sort and the most efficient way. So we keep actually shifting these items, all of the items which are bigger than this temporal value, this one that we are going to actually just insert in, you actually copy it in the a temporal variable, and then keep shifting all the values which are bigger than this temporal value until you find the correct position for this value. So this example here shows you that, for example, we have two values of 14, and what would happen to the sorting algorithm. So my question for you here is that to pause the video and think that if the insertion sort is a stable sort or not. So the answer is yes, insertion sort is stable. We can in fact implement it to be stable, and the way that we have implemented it here make it stable, because whenever you find an item which is equal to this item that you are inserting, so this previous value of 14 was equal to this value, right? And we actually have stopped before, and the new value of 14 will be inserted after the previous value of the 14. So yes, the insertion sort can be implemented. You can actually change this and remove the equality here, and then it will be unstable. But why not? We care about the sorting algorithms which are stable. So by adding this condition, keep it in this way, you can implement the insertion sort to be stable. And the next question is it in place? Yes, it is in place. You can see that we just actually used a couple of additional variables to implement the full algorithm, and we are not using additional space to store the items. So this is, we just actually use constant amount of space to store the items. So this sort is going to be in place. So the next question is, what is the time complexity? So you can actually again pause the video and check the time complexity based on the algorithm here. This is a very simple algorithm. You can just write down the time function for the algorithm and check the time complexity. The time complexity of this algorithm on average is going to be n power 2, and it is because of having these two actually loops. You can see that for every item, you might actually, every new item, just like this one, you might actually go down until to the beginning of the list, or even actually if you do it on average to the half of it, still this is going to be n square. So all the properties of this sorting, the insertion sort is very easy to implement, and in fact insertion sort is very efficient if the number of items that you are sorting is very small. So this is going to be really important for us. The best case time complexity for insertion sort is linear when your input is already actually sorted, but on the average and in the worst case, this is going to be n power 2. It is in place, it is stable, but again, I'm saying because the algorithm, you see the code looks very simple, and in fact, when you are sorting a small number of items, for example, something less than 50, usually insertion sort is going to be, if you have a good implementation of all this, insertion sort is going to be even faster than a merge sort or a quick sort. So in fact, that's why even in built-in functions of different programming languages for sorting, if the number of items is less than some threshold, they use insertion sort to sort to actually sort your array or the list that you are sorting. So that's why we are emphasizing on insertion sort and keep reviewing it. The next sorting algorithm that we have is merge sort. So we actually reviewed it in, I think, the second week when we talked about the time complexity of recursive algorithms. So the idea of the merge sort is that you actually divide it to two parts and sort each part, then merge them. My question here for you is that, do you think merge sort is stable or not? Pause the video, think about it, and then actually play the video again. So merge sort is in place. The reason is that the main actually part that change the order of the item is in the merging, right? So during the merge, you can in fact implement the method of the merge and make sure that merge will be done in a stable way. How? Just consider this this example, that you are merging these two arrays, right? And assume that you have two items here and here which are the same. And easily you can always, if you got two values which are equal, always take the one from the first part of the array. So in this way, the algorithm for merge will be stable, and the whole merge sort can be implemented in a stable way. So the time complexity of the merge sort, because of the recurrence relation was T of n equal to 2T of n divided by 2 plus n. So if you actually solve this is going to give you n log n. The fact is, for merge sort, there is no best case scenario, worst case scenario, or average. Always the sorting algorithm is going to do the same amount of work. Because you don't actually really care that if the input is already sorted or not. You always divide it to half, sort each part, merge them. So the same amount of work for every input that you actually pass to it. So it is stable, but is it in place? Maybe the only issue with merge sort is that it is not in place. You need additional space because of the merge, right? You remember that in the merge you need to have additional array to merge these two actually sub arrays, and because of this the merge sort is not in place. This is maybe the only disadvantage of merge. The main one. There is just a little bit compared to quick sort as well. So it is stable, it is not in place, and it has the time complexity of n log n, which is way better than n squared for the insertion sort. Okay, the next sorting algorithm that we have is going to be quick sort. Quick sort is, remember, it is a modification over merge sort. And the idea of the quick sort is that instead of always dividing the array to two parts in merge, you actually consider this array. So you find for example, choose a value as a pivot value. So some value, you take some value from the array, for example, as pivot, and what you do is to partition the whole items in the array in a way that the pivot value will be actually inserted at its correct position. So whatever is that correct position, you put it there, and all the values on the left part are going to be smaller than the pivot, and all the values on the right after the pivot are going to be greater than the pivot, right? So in this way, you don't need to merge these two half. So you actually, just like in the merge sort, you are going to recursively sort each part, but you do the partitioning instead of actually merging. In this way, we don't need to actually use additional array for the merge, and so quick sort will be in place. So the idea of the quick sort is to do the partitioning instead of merge, and in this way the algorithm will be in place. So solve that issue of additional space in the merge sort. The time complexity of that, remember, so that will be T of n equal to there will be actually some best case and some worst case. Everything will be depending on the pivot. So wherever is the rank of the pivot, so you will actually have something like this, T of n minus r plus T of r plus n. So that is actually going, let me actually see that. This is going to be the full reoccurrence relation, and based on the value of that rank, you can actually have the best case and the worst case. The best case is that if the pivot is close to the middle, so the relation will be 2t of n divided by 2 plus n, and if the pivot value is going to be close to the, for example, beginning of the array or the end of the array, so if the pivot actually comes to the close to the beginning of the array or the end of the array, so the relation will actually change to T of n minus 1, for example, plus n, because this part will be removed and this part will be T of n minus 1, or vice versa. And so this is going to give you actually the worst case, which the time complexity of that will be n power 2, although the time complexity of the best case will be n log n. Okay, so my question for you here is that, is quick sort stable or not? Again, you can actually pause the video, think about it, if it is stable or not. So you can see that in quick sort, the part that changes the order of the item is the partitioning part, where you actually find the correct position for the pivot, put it at its position, and then you change the position of all the items here and partition them around the pivot item. So you put all the items smaller to the left of it and all the items greater to the right of it. And because you are partitioning around the pivot, you have no control over the items to make sure that they will be kept in the original order if they are the same, if the order of them is the same. So because of that, the quicksort is not stable. It's not possible to implement quicksort in a stable way. So these are all the points about the quicksort. This is a kind of modification over the merge sort to make merge sort in place, so you don't need an additional array to sort the items. On the average case, it can be actually implemented to be in O of n log n. In the worst case, it can be n power 2 because of that, the order of the pivot. If you choose a bad pivot, it can be actually n power 2. It is not stable, but it is in place. There are actually good implementations of the quicksort, so that using actually the randomized quicksort to make sure it is going to always be O of n log n. If you compare merge sort and quicksort, they are very similar to each other, but quicksort on average is going to be faster than, although the time complexity of the average case for both of them is n log n, we usually actually prefer, it actually depends. For example, in the built-in function of Java, both quicksort and merge sort will be used. So in the cases that we don't care about the feature of stability, we prefer quicksort because it is using less amount of space, right? So if you are sorting a primitive data type, so for example, if you are sorting some integers, usually the assumption is that you don't care about the stability. So Java use the quicksort to sort the primitive data, the arrays of primitive data type. But if you are sorting some objects, it is assuming that the stability is going to be important. So some modified versions of the merge sort will be used in that case. And I just actually mentioned, if the number of items that you are sorting is smaller than some threshold, insertion sort will be used. So all of these three different actually sorting algorithms will be used in Java. The last sorting algorithm is heap sort. You have learned about it in COMP359. The idea of the heap sort is to use the binary heap data structure. Heap sort is going to be in place. It is not stable. You can again actually think about the whole algorithm, and you can actually review it from COMP359 or refer to your textbook. Chapter 6, I think, in your textbook is covering the data structure heap and also the heap sort. So it is not stable. The time complexity of the heap sort is going to be n log n in average case, and in the worst case, there is a best case scenario that if all the items that you have in your array are going to be of this, they are the same value, so the time complexity will be linear. That is going to be the best scenario. So otherwise, if they are distinct values, definitely it's going to always be n log n. What else? Although it is n log n, but quicksort and merge sort are faster than heap sort. And so heap sort is only actually used in the cases that you need the data structure heap and you also sorting the items. So kind of just in those cases heap sort will be used. Otherwise, quicksort and merge sort are going to be preferred over heap sort. Okay, so this is what we knew about the sorting algorithms. Now I'm going to slightly talk about the time complexity of these algorithms. So far, we have seen insertion sort, which was n square, and the three other sorting algorithms that all of them were n log n. So we wanted to know that if these sorting algorithms are the best sorting algorithms that we can have, or can we do better in terms of the time? Can we do, write some algorithms which are more efficient? Something about all these sorting algorithms that we have seen is that they are comparison sorts. What does this mean? It means that the only actual operation that we use, the only way that we get information about the order of the item is just by comparing them. So when you are actually sorting the items in all these four sorting algorithms that we discussed, we didn't assume any feature, any assumption about the input data. So we got the full information about the order by comparing the data. So you compare the elements against each other to find out which one is bigger than the other one, and sort the items and just change the order of the items to sort the item based on the comparison. So that's why we call them these sorting algorithms to be comparison sort. So there's something I wanted to actually talk about the time complexity of the comparison sorting algorithms and see that can we do better than n-log n. So far we know that there are some sorting algorithms, comparison sorting algorithms that works in n-log n. We wanted to see that is it possible to do better than n-log n, or n-log n is the best, is the optimal time complexity for sorting. So to do this, I'm going to use a specific structure which is called decision trees. So decision trees is, is a tool that helps us to abstract away all the details of the sorting and just care about, comparison of the items. Okay, so what is a decision tree? How we can actually create a decision tree? In fact, a decision tree is a binary tree that each node in this binary tree is a comparison of two elements in a sequence. And it is going to actually have, for example, if for each node, you are going to have two branches, two children, that the left one is showing. So for example, in each node showing comparison of two items in a sequence. So assume that you have a sequence of, for example, A1, A2 to AN. Each node has been actually labeled as I comparing to J, which actually means that you are comparing A sub I and A sub J, and you're comparing these two against each other, and the left edge shows that A sub I is smaller than or equal to A sub J, and the right actually branch shows that A sub I is greater than A sub J. So you might actually be confused. Let me actually show you a full, for example, decision tree for a sequence of 3 items. Just assume that I have arrays of size 3. For arrays of size 3, a decision tree, we can actually create a decision tree like this. And the decision tree will be actually, you can consider that for any length of a sequence. So for example, for size 3, the decision tree will be fixed because it actually covers any type of sequence. So I can actually just assume that for the root, I can compare the first item and the second item. Okay, so you are going to have two options. Either the first item is smaller than or equal to the second item, or the first item is greater. Okay, so if you are going to the left, then you compare the second item with the third item. Again, either it is going, the second item is smaller than or equal to the third item, or the second item is greater than the third item. So you are going to this way. So one thing about the, for example, the decision tree is that all the internal nodes are going to be comparison of two elements, and all the leaf nodes are telling me something. That, for example, if you started from the root and reach to this leaf node, it means that I get this information about the original sequence, that A sub 1 is smaller than A sub 2 and it is smaller than A sub 3. If you started from the root and you end up to this leaf node, it means that A sub 1 is smaller than A sub 3 and it is smaller or equal. You can actually just consider this. And this is going to be smaller than A sub 2. Okay, so each of these leaf nodes actually gives me an ordering of the original sequence, and the ordering is going to be the correct ordering. Just actually based on what is going to be the values of here. If you start from the root and you end up to any of these leaf nodes, that the label of the leaf node tell me exactly the correct order, the sorted order of the original array. So let me actually give you an example. Like for example, if the original sequence is 946, let's start from the root and see that where we are actually going to end up. You compare the first item and the second item. Okay, so 9 and 4. 9 is greater than 4, so you go to the right side, right? You compare the first item and the second item, and you go to the right if the first is greater than the second. And then you compare the first item with the third item. So the first item is 9, the third item is 6. Again, because the first item is greater than the third item, you go to the actually right. Okay? And then here you compare the second item and the third item. So you compare this one and this one. The second item is smaller than the third one, so you go to the left. Right? So you end up to this leaf node. The leaf node tells you the correct order is, the sorted order is A2, A3, A1. And if you actually check them, it's going to be 4, 6, 9. Okay, and this is exactly the sorted order of the original. So, in fact, the decision tree, each decision tree, if you actually create a decision tree for a sequence of length n, for example, shows you all of those comparisons that is required to find the correct order of the original of that sequence of length n. Okay, so it actually means that whatever is your input sequence, you need to start from the root and do a couple of comparisons until you reach to a leaf node. Sometimes you reach to a leaf node sooner, like for example this one, or sometimes you actually reach to the leaf node later, with more number of comparisons. But the number of comparisons that you do starting from the root node until to a leaf node is the number of comparisons that any comparison-based sorting algorithm needs to do. Okay, it's not talking about how the full sorting algorithm will work, but it just shows you the all that comparisons that the sorting algorithms needs to do. That's why I'm saying that decision tree abstract away the details of the sorting algorithm and just talk about the number of required comparisons, the number of comparisons that you need to do to find out what is the correct order of the original sequence. Okay, so now we are going to talk about decision trees and see that, so for example, if I have a sequence of n items, if I create the decision tree for that, how many comparisons you would need to check for any sequence of length n to find out the correct order. So the number of comparisons will be a path, the number of actually nodes starting from the root node until to a leaf node. Okay, so basically this is going to be the if you actually check it, this is going to be exactly the definition of the height of a binary tree. The distance from the root to a leaf node, the longest distance from a root to a leaf node, because you are looking for all possible sequences of length n, right? So that's why sometimes it is shorter, but sometimes longer. So you should consider the worst case. So for any sequence of length n, what is the worst case number of comparisons that you need to do to find out what is the correct order? Right? So that's going to be the height of this decision tree. So what we know about the decision tree? Decision tree is a binary tree, and a decision tree for sequence of different lengths are different. So if I have a sequence of length n, and if I create the decision tree, how many leaf nodes you are going to have in that decision tree? This is the question. So if you check the leaf nodes, you can see that each of these leaf nodes are going to be a permutation of the original sequence, right? So if you have a sequence of, for example, 1 to n, all different permutations of n numbers should be the leaf nodes of your decision tree. So based on this, how many leaf nodes you are going to have if you are creating decision tree for a decision tree for a sequence of n items, this is going to be n factorial, right? So in your binary tree, which is going to be actually a complete binary tree, a full binary tree, because all of the internal nodes are going to have two branches, two children, you are going to have n factorial number of leaf nodes. So now the question will be, these are all the information that we have, that we are going to actually talk about the decision trees. The height in the decision tree is going to be the worst case number of comparisons that any sorting algorithms needs to do. So we know that for a sequence of n items, the decision tree is going to have n factorial number of leaf nodes. Now our question is that what is going to be the height of a decision tree for a sequence of length n? So this is the question that we are going to ask. And this is to help us to find out the minimum amount of work that any comparison-based sorting algorithm needs to do. So I'm going to actually prove this theorem that any decision tree for n elements for a sequence of n items, the height of it is going to be greater than 2 n log n. Greater than or equal, let's just say that this is n log n is going to be the lower bound for the height of any decision tree for n elements. How we can actually prove this? So your decision tree is going to be a binary tree, right? And from COMP359, we know that in a binary tree of height h, the number of leaf nodes is going to be less than, so the number of leaf nodes is going to be less than or equal to 2 to the power of the height, the number of leaf nodes. Okay, so based on the height of the binary tree. This theorem, I think this is clear, but if you wanted to actually prove it, you can prove it using the induction. So the number of leaf nodes, number of leaf nodes in any binary tree is going to be less than or equal to any binary tree of height h, this is going to be less than 2 to the power of h. Okay, so what is going to be the number of leaf nodes in a decision tree? That's going to be n factorial, right? We know that this n factorial is going to be less than or equal to 2 to the power of h. And we are looking actually for that h. What is the value of that h? So what I can do here is to take the factorial, take the log from both sides of this formula. So this is going to be log of n factorial. It's going to be the height of the tree is going to be greater than the log of n factorial. I don't know what exactly this is going to be, but I know something, that n factorial is smaller than n power n, right? If I take the log from both sides of this relation, I will going to have this, that the log of n factorial is smaller than n log n, right? I actually took the log from this and I put that power outside, so this is going to be n log n. So I know that log of n factorial is going to be smaller than n log n. And the whole thing, this is going to be actually just smaller than, here you can actually put it as h. And so, in fact, I can actually find out that the height of the tree is going to be in fact, a lower bound for the height of the tree is going to be n log n for the height. And this is going to be, in fact, the lower bound for the quick sort. For any comparison-based sorting algorithm. And it actually tells us that already merge sort and heap sort are asymptotically optimal sorting algorithms that we can actually find. So here, actually, the whole discussion about the decision trees, you can find it in section 8.1, the theorem and the proof of that. Maybe I actually didn't explain it very well, but if you read your textbook, it's just actually 2 pages in your textbook, the section 8.1. You can read it there. For the review of the heap sort and quick sort, you can check section 6 and 7 from your textbook, or I will actually just post the video to the lectures from COMP359 as well. So I'm going to finish this video, and in the next video we will talk about the sorting algorithms that works in linear time. Those are going to be completely different sorting algorithms, not comparison based.